folks. It's a pleasure to be here. I'd like to talk about some of the lessons we've learned building FlowMill, which is a monitoring solution for network monitoring solutions, now part of Splunk. I'd like to discuss the question, how can we build observability systems that can handle large data volumes efficiently? And I've tried to take the lessons we learned that are more generalizable to the broader community and are not eBPF specific. So if you're building tracing, logging, or metric system, I hope this would be useful to you. I'm going to start by showing you some of the network data that is collected and why we chose eBPF to collect it. Look at some measurements of the volume that eBPF generates and the cost constraints on the system. And this motivated us to build solutions, techniques to handle this large data. And at the heart of these techniques is a domain-specific language that we call render, where developers can specify the schema of their observability system. I'll give more details as we talk about that. I'll then switch gears and move from the collection side to the storage and query side, the database, and go through a retrospective of what we did to scale Prometheus and what was still lacking there. I hope to take a step back and then discuss what would these capabilities of handling large data volumes at scale efficiently could open for our community in terms of use cases. So when you think about building a network monitoring solution, the first thing you think about is let's get measurements of sockets, the communication between components of the system, and we can get information about throughput, packet drops, latency, and such. But socket data is not as useful for users, we found. Users want to have the context of the communication. In this case, maybe the process, the container, and the host that traffic is coming from and terminating into, so both sides of the connection. And even that is frequently not sufficient. You want more context in the form of information about the VPC or the machine from instance metadata, information from Docker and your orchestrator, and information about address translation that is happening to traffic, and a mapping from external addresses down to names that users can identify, maybe from the cloud or DNS. Traditionally, collecting network metrics is done from the network. But unfortunately, by the time that application data hits the network, most of the context is lost. Instead of seeing the process and container, you see IP addresses and ports, and reassembling this context, especially in a microservice environment, is hard for observability systems. Also, collecting from the network has relatively high friction. On-prem, operators need to modify switch configuration to extract telemetry, which is not as easy as just deploying software. And in the cloud, access to detailed network data, it can become very, very expensive. In our community, many observability systems are built around instrumenting applications, for example, tracing, logs, and metrics. And instrumenting applications gets you great application context. But applications don't have ready access to the low-level metrics like packet drops, high network latency, or DNS failures. And also modifying individual applications can impose friction to deployment. In contrast, the operating system sits between applications and the network. So it has visibility both into the application context in the form of process and container, and the low-level networking information. And with eBPF, it is possible to deploy these systems like you deploy software. So that has very low friction. You can instrument every application running on a node and get network information for that without changing individual applications. But eBPF generates a relatively high volume of event data. Here you can see measurement from two different production clusters, one with running containers and one without containers. And you can see that eBPF instrumentation generates between 1,600 and 5,700 messages per node per second. Compared with tracing, network instrumentation can be similar or higher volume, and there are two reasons for that. One, for every span from tracing indicating a cross-service call, there might be multiple throughput, latency, and packet drop messages from eBPF. And secondly, eBPF gets this 100% visibility across every application running in the operating system, including system services and every service interaction, whereas tracing systems frequently have a fraction of coverage. It could be large or small, but this means that eBPF might generate more traffic. Although eBPF generates similar or higher volumes of data compared to tracing, the expectation from users is that you'd be able to run the system at a significantly lower cost. More like collecting metric data, maybe tens or hundreds of metrics per node, but not as expensive as a full tracing system. The saving grace here is that the raw socket data is not as useful for operators to perform root cause analysis, so you don't need to save the raw socket data. So while there's higher volume, you don't need to save all of it, you can save aggregate, so that reduces some of the strain. Overall, the high volume and low cost requirements mean that there is huge pressure on reducing the cost per data point for collection and processing. And there is also smaller but still material pressure on the storage system. So now I want to talk a little bit about collection and processing and some of the techniques we use to reduce that, the cost per data point. When we started building the system, we were hunting for a messaging framework, a library to handle messaging. And we came across this benchmark conducted by the Flat Buffers team. The Flat Buffers team compared several of these messaging frameworks. As you can see, Protocol Buffers Lite, JSON, XML, and Flat Buffers. And they compared these frameworks to encoding with raw structs. Raw structs mean just saving data into memory without special encoding. So that is the ultimate low overhead in encoding and decoding. What they found is that raw structs are more than 15,000 times lower cost to decode than protocol buffers, and that raw structs are over 1,000 times cheaper to encode than protocol buffers Lite. Protocol buffers encode messages very efficiently. They do work in order to get very small encodings for fields, but after compression, the savings for protocol buffers compared to compressed raw structs was less than 10%. So you do all this work and the size is not significantly smaller. If you think that the benchmarks are representative of the networking data sets, then think back to the last slides where I showed that eBPF generates between 1,600 and 5,700 messages per second per node. The encoding number means that collectors would need to spend between 30% to 100% of a core on every node of your system. So almost a core for every node of your system just to encode networking-based messages. That is a lot per node. And if you look at the decoding numbers, then decoding all the messages from a 1,000-node cluster would take between 500 and 1,700 cores. Yikes! That is way, way too much as cost just to decode all these messages for a 1,000-node cluster, and it is outside the realm of feasibility for network monitoring. We needed something better. This led us to ask the question, can we get the nice properties that protocol buffers and similar libraries have, like forwards and backwards compatibility, and libraries that handle encoding and decoding, and also get the awesome performance that you get from raw structs. This motivated us to build Render, which is a language for specifying the schema of observability systems. The developer writes a file specifying what data the system collects, and a compiler that comes with the Render language compiles a library that handles encoding, decoding, forwards and backwards compatibility, state synchronization. I'll talk about these in the next few slides. For message encoding and decoding, the developer specifies the message fields. This will look familiar to you if you know protocol buffers or Thrift. So developer specifies the fields that the message has, and the compiler generates the struct that holds the message. The compiler also generates functions to encode messages for eBPF and C++. So here's how one of these function calls looks like. It's pretty straightforward. This is an eBPF function. And the compiler also generates these stubs for handler functions in C++. So the developer has to come in and just implement the handler logic, and the framework handles everything else, decoding, dispatching of messages, and so on. Using these structs, we were able to get super cheap encoding and decoding between eBPF code running inside the operating system and the collector process running in user space on the same machine. The eBPF code and the user space process are built together with the same build system, so we can ensure that they use the same version of the protocol, so the same struct, so they're compatible. But if you look at the broader system, you'd want forwards and backwards compatibility. You have, this is how a system is deployed to a Kubernetes cluster. On every node, you have a kernel collector that collects networking data using eBPF. There's also a Kubernetes collector that collects information about deployments, stateful sets, jobs, etc. And an AWS collector, generally a cloud collector, that collects information about network interfaces, for example, the names of RDS instances and elastic load balancers. There is a component called the reducer, which assembles all the data from the collectors, is assembled at the reducer. The reducer fuses it together, takes all the metadata from the metadata collectors and puts it together with the data, aggregates, and pushes out metrics. We wanted all of this communication between the collectors to the reducer to also benefit from the low overhead of encoding and decoding. And you know, one of the reasons protocol buffers and similar frameworks are so popular is because they handle this for users. With struct-based encoding, we had these two structs. So I'll go through an example. On the right-hand side is a struct that maybe the reducer is built with, that it expects. And on the left side is a previous version of the message that maybe a collector was built with. We need a way to translate between the two. Luckily, the render language, when it builds the struct, it also knows how the messages are laid out in memory. So it can produce descriptors. So here's an example of a descriptor. You can see for the left-hand side, version 1 of the message has field 1 in bytes 0 to 3, field number 5 in bytes 5 to 8. I'm doing it from memory because I can't see it very well. Here it is, 4 to 7, and so on. With descriptors for both versions of the messages, for two versions of the message, it is possible to construct what we call a copy table. So instructions to copy the common fields between the versions. In this case, you would copy bytes 0 to 3 in version 1 to bytes 0 to 3 in version 2. So those are field ID number 1. And you'd copy bytes 8 to 11 in version 1 to bytes 4 to 7 in version 2. That's field number 17. Given this copy table, after you have it, processing an individual message is very quick. You just need to run through the copy table and copy some bytes. In this way, we were able to front load a lot of the logic to decode messages to sometimes when the collector connects, and then message processing became much faster. We actually took this to the next step. And we built a component, the transform builder, that takes the copy table, the set of instructions, and instead of running through a system that interprets that copy table to translate between messages, it just in time compiles a translator function to do the translation. In this case, with this copy table, you'd need 2 loads of a word and 2 stores to save it to the destination struct. So this further accelerates individual message handling. Even when we had efficient message encoding and decoding, we had a huge source of cost, which was metadata. In a large production system, we measured that for every container in the system, there were thousands of process and socket messages and hundreds of thousands of socket measurements. This means that if we had encoded container information, container metadata on every socket measurement, we would have repeated the container metadata over and over and over again hundreds of thousands of times. And we would have spent all the CPU cycles and the message size in order to do that. So we wanted to avoid that. What we did was extend the render language so that a developer can specify basically the graph you see on the screen. They would specify that a socket has this and that metadata, and a socket belongs to a process. That a process has this and that metadata, and a process belongs to a container, and so on. The collector sends out these messages saying, here's a new socket with this metadata, here's a new new process with this metadata, here's a new container with the metadata, and also when the sockets, process, or container are closed. And the render compiler generates all of the bookkeeping code to track all the live entities in your system and clean up either when a socket, process, or container are closed or when a collector disconnects. It does all of that for the developer, so that the developer, when it handles a socket measurement, all of the metadata for that socket measurement is already available in the reducer in memory. And you only have to send each piece of metadata once. This also allowed us to build the eBPF instrumentation that was much more modular. If you think about it, if somebody tomorrow wants to build a file I/O collector and not a network collector, they can, instead of implementing the socket entity, they would implement a file descriptor entity, and they could reuse all of the process and container and host logic that we've already built. That means that all of the effort that the community puts into developing these collectors can be reused. It also means that if someone then extends some of this instrumentation, for example, you collect the Linux capabilities, the security context that the process is running under, all of the collectors built with that infrastructure can benefit. So this was a major bonus of building entities. So some of the takeaways from increasing the efficiency of collection systems. We had a language where you specify the schema, and using that language, we were able to use efficient struct-based encoding. We used descriptors so that the system can front-load a lot of the work of parsing messages, so that processing individual messages later can be much quicker as you have a lot of messages of the same type. Just-in-time translator compilation help accelerate that translation even further. And entities allowed us not to repeat metadata over and over and over. This allowed us to build a collection system for network telemetry that uses under 0.25% CPU and less than 1% network overhead in typical deployments, and where the reducer, to do everything it does on a 1,000-node cluster, takes between 20 and 40 cores. So far we discussed collection and processing of data. I'd like to switch gears and move to the storage and querying side of the system. So database, with a quick retrospective of how we scaled Prometheus. We started with a single Prometheus instance to scrape all of the reducer data. We found that Prometheus only handles each scrape in a single thread. The reducer produced more data than a single thread of Prometheus could handle, so Prometheus would fall behind. We then partitioned metrics to multiple buffers and offered that as multiple targets for Prometheus to scrape. This allowed Prometheus to utilize more than one thread, to utilize multiple threads to process this data, and got us some more scaling. The next bottleneck we encountered was that Prometheus was falling behind closing blocks. And Prometheus uses a single thread per Prometheus instance to close blocks and write them to disk. And when there is so much telemetry that is flowing into, so many metrics flowing into a Prometheus instance, that single thread doesn't keep up. So if you have a 2-hour block, it takes more than 2 hours to write out the block. And this means the data kept accumulating in memory, accumulating more and more and more until the out-of-memory killer would kill Prometheus. This was kind of a nefarious failure because when Prometheus is spun back up after the kill, it tries to read the logs again and again. So it's a loop that requires manual intervention. We solved this by scaling horizontally, partitioning the targets among multiple Prometheus instances. We used a sufficiently large number of Prometheus instances so that the single thread would be sufficient in order to close blocks. As we scaled horizontally and scheduled these Prometheus pods on different nodes in the cluster, the next bottleneck we encountered was that TCP was not ramping up fast enough. We weren't able to scrape fast enough over the network. So what we did was we wrote the data from the reducer to Kafka and wrote sidecars next to each Prometheus instance that stream the metric data from Kafka and make it available for Prometheus to scrape. This was our solution. This setup worked, but it had other issues. First, disaster recovery is not a first-class citizen with Prometheus, so we had to kind of build our own. We used Thanos and a handful of home-baked scripts. This setup doesn't have any replication, so whenever you upgrade Prometheus or have any kind of blip in the system, there's unavailability of data. We had to manually load balance the partitions and to avoid hot partitions and all the pain that entailed. But maybe the most painful issue was this loop. If one instance became overloaded and the thread closing the blocks became the bottleneck. So, okay, this was the database part. Why should we care about scaling database and scaling collection beyond eBPF and network monitoring? Common workflow for observability starts with an alert, which is then followed by these cycles of investigation and mitigation. And you end up with the sequence of mitigations that hopefully stabilize the system as you uncover more symptoms of the problem. The day after you stabilize the system, hopefully developers and engineers go back to and investigate some more and find the root cause of the bug, missing safety mechanisms, or missing process. And the more detailed the data set that the observability system offers users, the easier it becomes to investigate a broader set of failures and not resort to moving outside the observability system in order to get that data. So let me go through some examples with network monitoring. With the node data set, a user can find if there's one node in the system with degraded networking. So maybe a hypervisor failure causes that instance to have dramatically lower throughput than other nodes. With pod granularity, it is possible to find failures where a handful of your pods are allocated next to noisy neighbors, offering a lot of network load onto the node networking systems. And so those pods allocated next to noisy neighbors might have worse P95 latency. So that node data set would not be sufficient. You need the pod data set, pod granularity information. With even more information about individual API calls, it's possible to find things like an important service was configured to try to reach out to an on-prem replica of a service and not the cloud replica of the service, and it didn't have permissions to access the on-prem data center. And so that results in a lot of timeouts. You can fix that. And if you compare this to tracing, taking a step back, tracing also, distributed tracing traditionally has this API call boundary detail. But imagine if you could instrument more. What if every function call that a service makes was observable? Not just the cross API boundaries, but every function call. Taking it a step further, what if every if statement that your service executes was observable? Or, to the extreme, if every code line that your service executed was observable. How much easier would it be with increased detail levels for developers to hunt down bugs and performance degradations without leaving the observability systems, without trying to trigger these complex failure modes on their laptops or in small development or staging environments? This could dramatically improve how engineers approach these problems and failures and how they fix and maintain their code. With the experience we've had with the eBPF collector and the reducer, I have confidence that building collection systems for these more intensive data sets is viable. We will be able as a community, I believe, to build these very intensive collection systems with low overhead, low cost per data point. What I think is missing and we should consider solving are databases that are able to handle this data. We need databases that can handle 100 times more data volume at similar cost to what they run today. So in other words, 100 times more data points at 100 times less cost per data point. And I think opening up the more intensive data sets is something that, as a community, we should try to look forward to, and we should try to tackle this database problem. With that, I'm happy to take questions, if there's time. Do we have time?
Yeah, we have time.
I know this is a lot. And it's before lunch, but I'm here.
All right, we got a question. All right. I was worried about that. Everyone just wanted to eat lunch.
In this slide just here, how much of that 100x scale at same cost do you think is achievable based on current storage prices? Or does storage have to significantly shift as well? Is it as much cost in the database or in the storage layer?
Mm-hmm. So I'll repeat the question. I'll paraphrase, sorry. So can storage, the current state of storage costs support the more intensive use cases at lower cost, right? Are we, as far as I understand, are we bounded by storage costs? I think we're not yet quite bounded by the actual storage because we have recourse in cheaper levels of storage that is less accessible. So personally, I think that if we build systems that can tier storage to the right cost of storage, so between kind of more of your distributed block, local network-based block storage, NVMe, RAM, and systems like S3 and GCS. Between those, I think there is cost savings to be had. I think a lot of systems today pay for the higher cost, higher levels of service storage for a lot of storage that they don't have to. And so we're not bounded by hardware yet. Great question, thank you. Another question over there.
Any challenges scaling your reducer to 1,000 nodes?
Was the question, did we have any trouble scaling the reducer to 1,000 nodes? Yes, of course. This was very fun to work on. So how do you scale one system that is able to process that much telemetry? The threading model, by the way, we are open sourcing this as part of OpenTelemetry. It's in the process of being contributed. To be able to handle this telemetry, we had this threading model where there was no locking between threads. We added in-memory queues, these rings, the ring buffers between different cores of the system, and we had a pipeline where each pipeline might have 10 or 15 or 20 cores. We have 3 stages of the pipeline, one for ingest, one for matching, so getting the 2 flows of every side of the socket together and adding metadata from Kubernetes and AWS, and then another stage of the pipeline for aggregation. And we used in-memory queues between them. Every thread can do bulk work. So you read a bulk of memory from the in-memory queues, you do a bunch of processing on this data, and you move on. Maybe sending some messages downstream to the pipeline. And that architecture enabled us to scale the system quite a bit. So to handle multiple, tens of millions of messages, some of them generated internally between components of the pipeline per second on a single node.
Awesome. Any other questions? Great. All right, we'll have one more round of applause here. We're going to be coming back at 2 o'clock. If you are looking for lunch ideas, lunch party in Slack. But otherwise, we'll see you all back here at 2 p.m. Thank you.